Let's head to the Middle East. There's a large desert here, and it's completely dark, except for one spot. It's a big circle that glows with a bright orange light, the Darvaza crater, and it's just a giant gas burner. Years ago, geologists found gas here, and they started mining for it. But when they excavated, they came across a void underground. The void collapsed, and it formed a crater. It's as wide as half a soccer field, and as deep as a 5-story building. Gas began to come out of the cracks in the crater, and since animals were often grazing near this place, the geologists decided to set these gas streams on fire to exhaust the source. Geologists thought the fire would be over in a day or two, but if you come here now, you'll see this gateway to the underworld is still burning, and it's been going on for almost 50 years. In 2013, a man descended to the bottom of the burning crater for the first time. He collected many different samples there, and scientists were able to find bacteria that aren't found anywhere else on Earth. They're quite comfortable at the bottom of this endless burning frying pan. In 2009, a man in L'Aquila, Italy, saw flickering lights dancing above the stone street. He immediately knew what to do and moved his family to a safer place. Only seconds later, a massive 8.3 magnitude earthquake hit the whole region. His knowledge of the strange lights saved his and his family's lives. So, what are those mysterious warnings? For centuries, people interpreted the lights as something otherworldly. The scientific community didn't take them seriously, just put them down to a false recollection, a mind trick, or pure imagination. With the introduction of surveillance cameras and smartphones, the amount of evidence grew enormously. Now the connection was obvious. Lights appear and an earthquake hits. So, experts finally started taking it seriously and started digging for the truth. But after years of research, to this day, geologists are still not fully sure what the source of the lights is. But they have recognized 5 types of them. Bright flashes that light up the sky, looking like storm lightning or a strong camera flash. Rays in the sky that can look like light columns. Different sized flames that come through the ground. Diffused glows over the mountains. And slow-moving balls of light that can be misinterpreted as ball lightning. Another equally little understood atmospheric phenomenon. These are literal balls of lightning that can float and explode, leaving a sulfuric odor behind. But unlike ball lightning, these spherical EQLs seem to be harmless, if you don't count what's coming afterward. But with all these types of lights, experts can't know how exactly they're connected to earthquakes. They don't only show up before one hits. Some have been reported during and after earthquakes. They can also appear with other phenomena, like meteorite crashes, volcanic eruptions, or auroras. For now, scientists can only come up with theories to explain the unexplainable. One of the recent ones claimed the lights were electric lines being broken during an earthquake. But this theory doesn't explain how the phenomena was observed hundreds or even thousands of years ago. Like the ancient Chinese tale of dragon-looking clouds appearing in the sky as a warning of an upcoming quake. Or how an ancient Roman historian reported huge flame-like lights bursting out just before a huge earthquake occurred. The electric line theory was quickly dismissed. Another theory suggested it was escaping gas. During an earthquake, the underground rocks expand and shrink under pressure and heat. This opens and closes small spaces between them. Different gases make their way through these new openings. Radon, for example, can get released during seismic activity. It can ionize the air, making it electrically charged. But radon doesn't do it enough to create bright sparks of light. This theory is close, but doesn't quite hit the mark. One of the most accepted theories is that it might be from electricity traveling up from underground. When underground igneous rocks, ones that form from magma deep within the earth, are under stress, they release ionized, or electrically charged, oxygen. It travels through the surface and up into the atmosphere, where it creates a localized electric field. That can produce brief flashes of visible light. Some aren't even that quick, and can go on for minutes at a time. So, there you are. You've been driving for hours through the night. You didn't have any chance to sleep, so your mind is hanging by a thread. You stop the car and go out to stretch your limbs. And then, you look up into the sky and see a beautiful sunrise. Whoa, wait! There are 3 suns in the sky! You rub your eyes, but nope. There are still 3 bright stars in the sky. No, our home star hasn't been torn into 3 pieces, nor has it been visited by 2 other stars. This is called a sundog. It occurs mostly during severe frosts. Small ice crystals in the sky bend the light. As a result, you may see 3 bright spots in the sky instead of just 1. This phenomenon is officially called a halo. Usually, it's just a circle around the sun. You can even see a halo at night, too. Just look at a street lamp, and you'll see a bright circle around it. Sometimes, a halo can take on a fancier shape. If there's a lot of ice in the air, the light is warped even more. Just like in a room with a dozen mirrors. Then, the halo can take on the shape of a human eye. Because of this phenomenon, a false dawn can occur too. While you're looking at the horizon, the dawn begins, and the edge of the sun appears. A little bit more, and wait, the sun starts to just dissolve in the sky. After a few moments, it's dark again. And only a minute later, the real sun shows its face. It was the same light curvature effect you saw before with the 3 suns. Only now, the light is curved vertically, not horizontally. And instead of the real sun, its reflection in ice crystals in the sky appeared. And now moving on. This cloud looks like a dinosaur, and this one looks like a cat. And this, whoa, it looks like these clouds are falling down. Oh, phew, that's just a mammatus cloud. Their shape really makes them look like chunks of cloud about to slam on the ground. Well, that's not going to happen, but you better start seeking cover anyway. Such clouds are a sign of a severe thunderstorm coming. It takes a lot of moist air with ice crystals at the top and dry air at the bottom to create such clouds. Then, vertical currents of air appear between these layers. And these currents make the clouds take the shape of a human brain. And this giant cloud looks like a dome that's going to cover an entire city. In fact, that's exactly what happens. A huge cloud covers a large area and then rains heavily on it. Sometimes, the front of such a cloud takes a bizarre shape, like in these pictures. It looks more like several giant spaghetti clouds, or even giant cloud worms. This phenomenon can often be seen in Australia, and it's called morning glory. It happens because a strong wind twists part of the cloud on both sides, and then the huge sheet of air dough splits into thick strips. And sometimes, you can see clouds in the sky made of birds. Wow, that cloud moves quickly and changes shape. It becomes more transparent, but then denser and darker again. The birds seem to be involved in some kind of dance or performance, but they're not doing it for beauty or for the crowds of spectators gathered below. They're doing it for protection. When birds group themselves into such a cloud, they intimidate birds of prey. An eagle or hawk would have a hard time picking out a single target among the endless number of birds. And they move quickly, covering each other. Fish are huddled together in schools in the same way. Such a cloud might just spook a hungry predator. Grab some sunglasses and you're good to go. This phenomenon lasts around 40 minutes. These clouds are the same ones that can cause a spooky ring around the moon at night sometimes. Nature sends early signs of disasters in many different ways. J-shaped trees might mean there's a landslide coming. Since the ground is moving slowly, the trees grow into this super selfieable shape. Try to find a flat area and avoid going near any trees unless you have superhuman strength. Another mystical phenomenon can be seen in the desert, a sand waterfall. When the wind brings a lot of sand to the edge of the canyon, it begins to fall down. Now amplify this effect 100 times and you get a sand waterfall in Saudi Arabia. It's really like Niagara Falls, only there's not a drop of water. The locals say this phenomenon warns of an impending sandstorm. The speed of light is the fastest thing in our universe. It travels across space, passing through Mercury and Venus to reach us, and it's slowing down. No need to panic though. The sun is getting weaker, but we won't see the effects of it for another billion years. In the vacuum of space, the speed of light is around 186,280 miles per second. Any slower than that, and humans would see the changes firsthand. There would be some awesome effects, like colors changing and the brightness of objects fading. We'd also notice some differences in everyday objects, their length and shape. Scientists created a simulation to see what would happen if the speed of light was slower. In a vacuum, the speed of light can't change, but if light passes through different materials and objects, it alters the way we perceive things. Light acts as a wave and a particle, meaning that it's a wavelength. The color and frequency are determined by the distance from crest to crest in the wave. It behaves similar to sound with the Doppler effect. Imagine you're standing in the middle of a busy highway and a honking car speeds through. Wow, that was loud. You can hear that whoosh-like sound of the horn because the moving object produces the sound while you're stationary. The frequency and pitch seem to change, but it's just the sound reaching your ear faster than it would if you and the car were both stationary. Light behaves similarly. The wavelengths change if the speed changes. Moving toward a light source and making the wavelength shorter will shift the color to a blue and violet hue. Moving away from the light source, and you'll get something more reddish. So if the speed of light slowed down to walking speed, we'd notice the colors changing when we approach an illuminated object. At the same time, the color would change around us and behind us. If you walk sideways, the colors you're walking toward would become bluer, and everything in the distance would become red. This information is useful to astronomers who are studying objects in space. If they're blue shifted, that means the object is moving towards us. And if it's red shifted, then it's going in the opposite direction. In fact, everything in the universe is red shifted, proving that the universe is expanding and getting further away from us. The slower it gets, the brighter it becomes. That's because the photons become more present for us to see. At this rate, we can see invisible light and increased intensity. You won't notice that effect much if you're standing still, but because of the Doppler effect, moving towards an object will have different colors and different light intensities. Another phenomenon we'd experience is time dilation. It's when you move at a similar speed as light and time decreases relative to someone who isn't. Space and time are relative. So if you're sitting at your desk wasting hours away, yeah, sounds familiar, doesn't it? All your movement will go through time and not through space. You're stationary, but you're still technically moving forward in time, slowly aging. The faster you move through space, the slower your movement through time will be. If you move at the same speed as light, then all your movement will be through space and not through time. To notice that, you'd need another person to watch you. You're not in a time machine. You're both on Earth experiencing the same time flow. To you, experiencing this firsthand makes it feel like you're going faster, because you're getting a lot more movement in space in a given time. The closer you get to the speed of light, the smaller you become. Well, not really, but it depends on who's watching. If you're the one traveling at such a speed, an object nearby will seem small, just as someone who's watching you travel at the speed of light will think that you're smaller than you actually are. The simulation that the MIT scientists conducted showed that if the speed of light drops, everything will become stretched out like a pancake. If you see mountains in the distance and then run at the speed of light, they will appear further away. Objects will become distorted, and it will feel like you're getting to a certain place faster because time has slowed down for you. If you're standing completely still and someone standing on your left-hand side throws a cube-shaped object over to your right-hand side, then naturally, you'll see one side of it unless it flips around. But in this new reality, you'll get to see the front side wrapping around the visible side you're seeing. If you're moving at the same speed as light in an infinite space, Everything will be stretched out as you reach infinite speeds. In a world where people can walk at the same speed as light, we'll perceive nothing as normal. We'll have to get used to the way we see objects. Every movement we make will result in drastic shifts of colors. Even turning your head to look at something will feel weird. Let's say you're in a supermarket buying groceries, and you walk from aisle to aisle. The milk at the end of the counter will look like it's really close to you. But when you approach it, you'll start to feel like it's getting further away from you. The milk will also look a bit red. As soon as you get closer to it, it will shift to blue. If someone is passing through with a shopping cart, you'll see it as a sort of 3D model of a shopping cart. The color will shift as it gets further away from you. It will appear far away, but it's right in front of you. In fact, we don't really know the actual speed of light. Physicists gave it roughly 186,280 miles per second, but that constant is just for them to calculate other scientific stuff so we can understand it better. The problem is that we can only measure light with light beams and mirrors. But it's not like all we have to do is point a light beam at a mirror and measure its original path and its reflected path. Einstein's theory of relativity states that the original path of light moving from the source to the mirror may not be the same speed as the reflected light from the mirror back to the source. Hypothetically, if it takes light 10 seconds to travel from the source to the mirror and then back to the source, then we can conclude that each trip takes 5 seconds. But Einstein's theory is that it could take 9 seconds for light to travel from the source to the mirror and only 1 second from the mirror back to the source. Or vice versa. Or maybe completely different numbers altogether. That's why it's so difficult to measure light. A breakthrough came out for scientists when they managed to slow down the speed of light to 0 without losing its brightness. They did this by using ultra-cold atom clouds made with photonic crystals. These crystals are materials punctured with billions of tiny holes where light can refract. But what if we lived in a world where light stopped halfway? You'd wake up one morning and feel like it's twilight. You'd open the curtains and see that many car lights are on, but aren't so bright. You turn on the lights in your room, but feel like the bulb is tapping out. You replace it with another one, but it doesn't do the trick. You turn on the lights everywhere in your house, but it's all just giving weak light. You're confused and try to check if there's a problem with the electricity in your house, but it seems to be working well. You check on your neighbors, and they also have the same problems. Even experts in the field can't understand what's going on. Hours pass, and it's all the same. All the light in the world seems to have frozen halfway. Your phone is low on brightness, even though you bumped it up to maximum. Everything is getting darker. You learn from the news that it's a global problem. Light is slowly diminishing, and soon there won't be any of it in the world. You decide to wait it out while everyone else is panicking. You're flying above Earth on the International Space Station at an altitude of 250 miles. You cast a glance out the porthole, and your eyes widen in surprise. There's some kind of bright blue flash just above nighttime Europe. It's like there was an explosion of some strange substance there. Such a strange luminous event was spotted by a French astronaut from aboard the ISS. And it wasn't an explosion at all. It was lightning, and was directed upwards. Until recently, this phenomenon was a kind of fairy tale among pilots. Scientists had heard their stories about lightning striking upward, and about red and blue flashes at high altitudes too. But there was no definitive proof of the existence of these luminous events. But they do exist, and are called sprites, elves, trolls, and ghosts. So how does ordinary lightning work? Masses of moist air in a cloud rub against each other and create static electricity. It would be almost the same if you danced in a wool sweater. It becomes charged with static electricity. And if you touch a metal doorknob, there's a discharge between your fingers and the door. There's your lightning. So a thundercloud builds up a strong negative charge. Sooner or later, a leader is born in the cloud. It's a bright thermo-ionized channel, or more simply, lightning. The leader moves toward the ground in steps of a few tens of feet, and it can accelerate to an average speed of 200,000 miles per hour. At that speed, you could make a trip around the Earth in just 7 minutes. But negative particles attract positive particles, and particles with opposite charges will tend to connect and compensate for each other. So, simultaneously with the negatively charged leader, the positive charge from the Earth begins its upward journey. The electric charge from the Earth connects with the negatively charged leader in one channel. This is when the brightest and loudest discharge happens. We call it lightning. It's this discharge that you hear as thunder. The main lightning doesn't strike from top to bottom, but from bottom to top. Yep, that is, the lightning is actually directed upward. It's as if the Earth is striking back at the thundercloud. And that charge can reach up to 30,000 amps. Your average wall outlet only has about 15 amps. And the record for the length of lightning is about 440 miles. That's more than the width of the state of Kansas. Meteorologists recorded such lightning in Brazil. It was a discharge between giant thunderclouds. And the longest lightning strike was recorded in Argentina. A single lightning strike there lasted 16.3 seconds. By comparison, you blink at 0.1 seconds. So we saw a regular lightning strike. The positive particles from the ground neutralize the negative particles in the cloud. But the cloud is still full of positively charged particles. They accumulate and wait for their time to create lightning. Once the charge reaches a critical point, the lightning cloud throws that charge dozens of miles upward. This is called a blue jet. It's exactly the same luminous event seen by a French astronaut aboard the International Space Station. The blue jets look like someone turned on a gas burner pointing upward. The positively charged blue jets neutralize at high altitudes with negatively charged particles, but people on the ground cannot observe blue jets. Thunderclouds obstruct the view, but they can be seen from an airplane. That's why, for a long time, commercial airline pilots were the only witnesses to this phenomenon. On board the ISS is also a great place to observe jets, as they are born at the very top of thick clouds and shoot dozens of miles upwards. But if you climb even higher, you can see this kind of bizarre lightning. It's a sprite. It looks more like a jellyfish. A cloud of red charge at the top and a bunch of little tentacles coming down. Now, normal lightning can have a temperature of about 54,000 degrees Fahrenheit, but you can touch a sprite with your hands. Unless, of course, you're afraid of a powerful electrical discharge. The sprite has about the same temperature as an energy-saving light bulb. All because sprites are born in the mesosphere. This is the layer of our atmosphere that starts at about 31 miles high. And it's the coldest place on our planet. On the ground level, where we live, the air is much denser. There are just more air molecules. They absorb heat from the sun's rays, and we feel comfortable. But the higher up we go, the fewer air molecules there are. At the altitude at which commercial airline planes fly, there's no longer enough air to accumulate that heat. You wouldn't even be able to breathe up there. That's why every airplane has oxygen masks for emergencies. And the temperature here is even colder than at the South Pole. In the mesosphere, there's almost no air, and the temperature here can be around negative 202 degrees Fahrenheit. And although the temperature of the lightning itself is high, in general, it's like if you poured a glass of boiling water into a huge barrel of cold water. The temperature won't change much. Sprites can only appear when paired with thunderclouds below. As a discharge occurs in a cloud, a sprite appears in the mesosphere. It tries to equalize the amount of charge in the atmosphere. So it's like these red flashes of lightning are trying to reach down to the thunderstorm. And a sprite itself can be as wide as the state of Massachusetts. And then there's a ghost. It can appear for the tiniest fraction of a second right after the sprite. It's a faint green glow, like an aurora. They were first discovered in 2014, and official confirmation by the scientific community only appeared in 2019. They're still poorly understood, but there's a hypothesis that ghosts have something in common with auroras. At least their color is green, and it may arise due to excited oxygen atoms. Sometimes we can spot trolls along with sprites. They look like pillars that support a sprite. It's a red glow at the end of the sprite's tentacles. The next moment, the troll releases a red streak down from itself. And if we climb even higher, we can see the elves. They only appear for 1 millisecond. It's a dim, flat glow that appears during thunderstorms in the ionosphere at an altitude of about 62 miles above sea level. Elves can be as wide as the distance between New York and Washington, D.C. Elves were first discovered during space shuttle flights in 1990. And these are pixies. They weren't discovered until 2000. Scientists observed bright, brief, luminous events for 20 minutes. Although they looked like lightning striking inside a cloud, They have nothing to do with them. Pixies are smaller than 100 meters, which is about 330 feet. We shouldn't forget that any lightning is extremely dangerous for humans, and if you're caught in a severe thunderstorm, you need to leave its epicenter immediately. You can determine how far you are from the epicenter easily. The speed of light is much faster than the speed of sound. So, when lightning strikes, it takes a couple of seconds until you hear the thunder. So, you need to measure that interval. Lightning! Now count the seconds. Every second of thunder delay after lightning is about 1,150 feet. That's the distance a wave of sound travels in 1 second. So if the thunder delay after a lightning strike is 5 seconds, you're about 1 mile from the lightning. You can also tell if there will be a thunderstorm by the smell. The air before a thunderstorm seems unusually fresh. This is because the air currents bring in ozone molecules from the upper atmosphere. The same ozone protects us from harmful ultraviolet rays and transfers heat from the sun to the atmosphere. What we use to breathe is the oxygen of 2 atoms. Add 1 more and you get ozone. Ultraviolet light breaks down the 2 oxygen atoms and is absorbed by them. These broken atoms are then attached to the normal double oxygen atoms. When an ultraviolet beam strikes an ozone molecule, it knocks 1 oxygen atom out of the chain again. But ozone tends to regenerate, so the lost oxygen is reattached to other double atoms. But the ozone layer began getting damaged when humanity started emitting harmful gas into the atmosphere. Freon is to blame. It's the gas we were using in old refrigerators. The freon molecule contains harmful chlorine atoms. Ultraviolet rays knock this atom out of the molecule. Then that chlorine atom steals 1 oxygen atom from ozone, and we have a double oxygen molecule that can't regenerate and save us from the harmful ultraviolet rays. This causes a hole to appear in the ozone layer. The most famous ozone hole was over Antarctica, but when humanity banned the use of harmful chemicals, this hole began to recover. It's not that the hole will close completely, it will just return to the way it was before.